So I'll start with preliminaries of Hertzian dipole for Hertzian dipole, and we'll revisit some of the portions that we discussed in the last class. So one of that was time harmonic function. This we discussed in the last class. Now suppose W is a function of space and time. WRT is a spatio-temporal function. W is a function of space R and time T. Then it is said to be time harmonic or harmonic in time if it contains only one frequency. That is the first condition, that it should contain only one frequency. And usually we represent the time part, time dependent part of W as suppose Wt is equal to cos omega t plus phi with a constant or with an amplitude. Now as you know, cos theta is equal to exponential real part of exponential j theta. Therefore cos omega t plus phi, that you can represent as exponential j omega t into exponential j phi. So time part will be exponential j of phi into exponential j omega t. So that is what it is. It can be exponential j omega t part can be plus minus, because as you know e to the power plus theta or minus theta, for both the case, if you take real part, that gives you cos theta. So e to the power plus theta or minus theta, real part of that gives you cos theta. Therefore it can be the variation, time variation can be of the form exponential j omega t. So now as you know, we have already discussed how to find out the vector potential, and for vector potential the expression that we have found out both for vector potential and scalar potential, we have seen that vector potential we can get from current density or current, scalar potential we can get from charge density or charge. We are going to consider only vector potential here. So vector potential A is a function, spatio-temporal function, and let us assume that A is a time harmonic function. So we'll find out what is the expression for A when it is time harmonic function. So ART is the vector potential that we can write as 1 by 4 pi integration mu j r dash t dash, where t dash is equal to t minus r by c and t dash is the retarded time. So A is equal to mu j as a function of r dash t dash divided by capital R. Capital R is the distance between the source and the observation point, that into dv over integration over volume, and so dq r dash, that takes care of integration over volume. So now we can see that ART, A is a function of A is a spatio-temporal function, and on the right hand side mu is not a spatio-temporal function, R is not a spatio-temporal function, pi is also not a function, pi is a constant, mu is usually constant, R is only a function of space. The spatio-temporal function is J. So on J we can write as j r dash t dash, that we can write as j r dash into exponential j t dash, exponential j omega t dash. So if we write in that manner, and ART is equal to AR exponential j omega t, since ART is a time harmonic function, you can separate it into spatial part, temporal part, and temporal part variation is of the form exponential j omega t. Similarly, for the uh, small j or the current density, which is a spatiotemporal function that you can divide into spatial part j r dash and temporal part j, exponential j at omega t dash or j omega t minus r by c. T dash is equal to t minus r by c. So if we do that within the integration, we have exponential j omega t. So and integration is over volume. J omega t does not vary with space. It is constant with respect to space. It is a function of time. So that we can take outside the integration side. So left side now becomes a as a function of r into exponential j omega t, and right side becomes exponential j omega t by 4 pi outside the integration, then integration of mu on j as a function of r dash, then exponential j omega exponential minus j omega by c into r. Now omega by c is equal to k, therefore that term becomes exponential minus j k into r. Denominator is capital R and integration over volume. Now on left hand side and right hand side we have exponential j omega t, which cancels out, leaving out ar is equal to 1 by 4 pi exponential mu j as a function of r dash exponential minus jkr divided by capital R integrated over volume. Now this is the spatial part of the vector function or vector potential A. So vector potential A, when it is represented in time harmonic form, then we have its spatial part, we have its temporal part. Temporal part varies as exponential j omega t, and spatial part is given as ar as a function of r, that is called to 1 by 4 pi volume integral of mu j as a function of r dash exponential minus jk r minus jk capital R divided by capital R, where capital R is the distance between the source and the observation. R dash is the position vector of the source. So this is the spatial part. Then multiply that with exponential j omega t, that will give you the complete vector. So how will be concerning since e to the power j omega t, that we know now is at our hand. So that will keep aside. We will only deal with AR or only the spatial part. Okay. Next. Next. Now let us come to, from that we will come to the time harmonic Lorenz condition. Time harmonic vector potential, we have seen what is the expression for time harmonic vector potential. Now let us consider the time harmonic and Lorenz condition. The Lorenz condition is divergence of ART plus 1 by c square dou t phi RT is equal to 0. This is what is the Lorenz condition. Now ART is time harmonic, phi RT is time harmonic. Therefore ART and phi RT can be written as ART will be AR exponential j omega t, phi RT will be phi R exponential j omega t. So if we write in that manner, then the first part is divergence of AR, because divergence will operate only on the spatial part. So spatial part is AR. So divergence of AR whole into exponential j omega t plus 1 by c square dou t phi R exponential j omega t. Now dou t is a temporal operator. It operates on time only. So phi r can be taken outside dou t. So dou t will operate only on exponential j omega t. Dou t operating on exponential j omega t gives us j omega into exponential j omega t. So using that we will get in the third line that you can see, in the third line we get divergence of AR exponential j omega t, that part remains as it is, plus from differentiation we got the j omega divided by c square remains as it is, phi r remains as it is because dou t is not operating on that. Then we have exponential j omega t that is equal to 0. Next. Now exponential j omega t is on both the terms. Since exponential j omega t is on both the terms, in the left hand side and right hand side is 0, and exponential j omega t is not equal to 0, therefore we can cancel it out from both the terms. So that will leave us divergence of A plus j omega by c square into phi is equal to 0. So this is the Lorenz condition in time harmonic form. So if you have time harmonic vector potential and time harmonic scalar potential, then the Lorenz condition reduces to divergence of A plus j omega by c square phi is equal to 0, from which you can get what is divergence of A in terms of phi. So divergence of A is equal to minus j omega by c square phi, and as you know, 1 by c square is equal to epsilon mu. So you can say divergence of A is equal to minus j omega epsilon mu into phi. Now once we know that, let us look at Helmholtz equation, time harmonic Helmholtz equation in the for the uh, vector potential. We know when we apply Lorenz condition, the vector potential obeys the Helmholtz equation. The Helmholtz equation is del square A minus 1 by c square, and dou t square A is equal to minus mu j. Now here what we will do is, A is a time harmonic for a function. Therefore for A we will write AR exponential j omega t. So this equation, the Helmholtz equation, original Helmholtz equation, which is operating on both time and frequency, now becomes del square AR exponential j omega t minus 1 by c square dou t square AR exponential j omega t is equal to minus mu into j, and j is now a spatiotemporal function. So j is equal to and jr into exponential j omega t. Now in the first term we have exponential j omega t, delta square will not operate on that. In the second term we have exponential j omega t, dou square t will operate on that, dou square t will not operate on AR. So that we will write, the second term we will write now as 1 by c square AR, these are constant with respect to t. So take them out, then dou square t operating on exponential j omega t is equal to minus mu j exponential j omega t. Now with the second derivative, taking the derivative, second derivative of exponential j omega t will give us minus omega square exponential j omega t. So we will drop out dou square t. So the equation now becomes del square A exponential j omega t minus 1 by c square A. When we say A now, it is AR. 1 by c square AR, A as a function of R, into minus omega square exponential j omega t is equal to minus mu on j as a function of R exponential j omega t. Now in the second term on the left hand side we have two minus signs, so that will become, the second term will be having a plus sign, minus minus becomes plus. So the equation now becomes del square AR exponential j omega t plus omega square by c square a as a function of r, that into exponential j omega t is equal to minus mu j as a function of r exponential j omega t. Now you look at on both the sides. On both the sides we have exponential j omega t, and exponential j omega t is not 0. So therefore that will cancel out. So if that cancels out, this will leave us with del square ar plus omega square by c square ar is equal to minus mu jr. Now you know omega by c is equal to k. So omega square by c square is equal to k square. So the Helmholtz equation now reduces to del square A as a function of R plus k square A as a function of R is equal to minus mu J as a function of R. So this is the Helmholtz equation. So now how to solve this Helmholtz equation? Once you get the Helmholtz equation, how we are going to solve the Helmholtz equation? Let us look at that. So if you look at the Helmholtz equation in the time harmonic form, it is del square AR plus k square AR is equal to minus mu JR. Now this is a second order differential equation, and this is a inhomogeneous equation, and it is a second order differential equation which is known as the wave equation, or which represents the wave propagation. So this equation is an inhomogeneous equation. Why it is called inhomogeneous equation? Because the right hand side is not equal to 0. If the right hand side is equal to 0, then we get a homogeneous equation, but the right hand side is not equal to 0, so that gives us an inhomogeneous equation. So this equation is an inhomogeneous equation. Now how to solve this equation? What we can do to solve this equation? And the solution is has certain parameters. Now look at the right hand side. Right hand side is JR. Now on JR, J is the current, which means it is the source. Now source is not present everywhere in the space. Source will be localized to one place. So source will be at R only. So source is source will be at R dash only. When R is equal to R dash, it will be there. Suppose we have R dash is at 0 at the origin. So the source, if we place source and origin at the same point, then the source is at the origin only. Otherwise source is 0. So the right hand side is actually 0 everywhere except at the origin. So this inhomogeneous equation in the space is actually a homogeneous equation except at the source. So at the source it is not 0, everywhere else it is 0, which means we can say that JR is a function which is 0 everywhere except at R is equal to 0. That means JR can be represented as a Dirac delta function. So on the right hand side can be a Dirac delta function. If the right hand side is a Dirac delta function in the above equation, if we put the right hand side as a Dirac delta function, then we say that this equation solves the wave equation for a Green's function. So A, the potential function, now becomes the Green's function. So what we have to do is, first we have to find out what is the Green function. So obtain the solution for Green function, replace A by G on the left hand side, that is the Green function, and on the right hand side replace mu J by delta R, delta Q bar, that is, since we are considering volume, so right hand side will be delta Q bar. So under that condition you solve this. Now what happens under that condition? If you remember your signals and systems or communication there, or even this one control, there you know something called impulse response. You have a system. This system is represented by H, capital H. If you give an impulse to the system as input, output is say small h. Okay, then we call small h as the response of the system to an impulse. And how do you find then? We can find out the response to any other input to the system by taking the convolution of the input with the impulse response. So here we will find out this. So here what we will do is use the same concept. Here the system is the radiating system or the free space radiation from the source. So the impulse is the excitation, and G for H we are taking G. G is the wave function. So now we can find out, for if we take the convolve J with G, that will give us A. So A is for any other input. What will be the response? That is A. So A we will get by convolving J with G. Now how to find out the green function? To find out the green function, we will replace A with G on the left hand side, replace the right hand side mu J, that is replaced by a delta function. Then we will find out the solution of the corresponding differential equation. So let us look at the solution of the Green function. Let us find out what is the Green function, find out the solution and find out the Green function. Now for Green function, what we are looking at, the solution of these two differential equations. We are trying to solve del square A plus k square A is equal to minus mu J, and for A we have replaced the Green's function. So that becomes del square G plus k square G is equal to, for the right hand side mu J we have replaced del QR. So that is equal to del QR. Now remember one thing here. The R's that I am using here are actually R dash, the source point. Everything is at the source, not at the observation, because at observation right hand side will go to 0. So these are all at source. The right hand side exists means these are all at source. So actually these are R dash, but for simplicity I have written it R. So you can write or note that all these R actually represent R dash or the location of the source. So these are on source, around the source. Now on this del square or the nabla operator, since we are using a source only, located at a point only, so therefore it will have a spherical symmetry. The source will have a spherical symmetry. If it has spherical symmetry, then del square will be easily represented in terms of the spherical coordinate system. So let us represent that in spherical coordinate system. If we represent that in spherical coordinate system, then del square becomes 1 by r square dou r operating on r square dou r gr plus 1 by r square sin theta dou theta operating on sin theta dou theta gr plus 1 by r square sin square theta dou square phi operating on gr plus second term is k square gr, and the right hand side is minus dqr. Now on the left hand side, if you look at the terms, the second term has a differential operator on theta, but it is operating on gr. Gr is a function of r only, since we are considering a source at the origin, or it is a point source at the origin. So it is symmetric about theta and symmetric about phi. So gr is not dependent on theta and phi. So gr is a function of r only. So dou theta operating on GR will give us 0. Similarly, dou phi operating on GR will give us 0. So dou theta and dou phi operations here, they give us 0. Dou theta is equal to 0, dou phi is equal to 0. So if you take that, then the second term and third term on the left hand side are 0, leaving us with the first term and the fourth term. So first term is 1 by r square dou r operating on r square dou r gr plus k square gr is the last term. So that is called to minus dou cube r. Now we have to solve this differential equation. To solve this differential equation, let us make a substitution here. The substitution is LR is equal to R into GR. Let us substitute R into GR with LR. If we substitute R into GR with LR, then we will get 1 by R square dou R square dou RGR, that becomes dou square R operating on LR, plus second one is K square operating on LR, that will be equal to 0 when we are considering the homogeneous part of this. That will be equal to 0 everywhere except at r is equal to 0, at s is equal to 0. Now if that is equal to 0, the solution, you know, this is a simple differential equation. Its solution will be LR is equal to C1 exponential minus JKR plus C2 exponential JKR. C1 and C2 are constants which we have to find out. Now here what we are doing is we are having a source, and from the source field is emanating outward. So nothing is coming towards the source. Since nothing is coming towards the source, we have a source from that field is emanating outward. Therefore, the second term exponential JKR, which is the term responsible for inward propagation, that will not be there, that will be 0. So that part should not contribute. So since e to the power JKR is not 0, so that part should not contribute, which means C2 should be 0. So LR is equal to C1 exponential JKR. So that is the condition that will take. Next. So LR will be C1 exponential JKR. Now LR is equal to R into GR. Therefore GR will be LR by R. So GR is equal to, Green's function is equal to 1 by R into C1 into exponential minus JKR. So that is what is GR. So if that is what is GR, then we are left with the choice of finding what is C1. So from physical conditions we have seen C2 is equal to 0 because there is no inward propagation. So that ensures C is equal to 0. And we are left with the choice of C1. We have to find out what will be C1. To find out C1, what we will do is, again we will go back to our original wave equation in GR. So use the original wave equation. In that equation, put for GR, we will put 1 by R C1 exponential minus JKR. Then take volume integral of both the sides of the wave equation. So that is what we are going to do. We will take volume integral of both the sides of the wave equation and put GR is equal to 1 by R C1 exponential minus JKR. Then as we know that the source is only at the origin, it is not expanding, or it has no expansion beyond origin. Therefore R is approaching 0. So what we will do is we will take the limit R goes to 0 on both the sides of this the integration. So on the left hand side we will get a limit R goes to 0 in volume integration. Volume integration is 0 to R and 0 to pi. 0 to R is in the R variation, 0 to pi in the theta variation, 0 to 2 pi in the phi variation. Then on the first part is in the of the differential equation is we have already seen 1 by r square dr operating on r square 2 dr into 1 by r c1 exponential minus jkr, or the dr operating on gr is equal to 1 by r c1 exponential minus jkr. Then the second term is k square into 1 by r then into g. So the gr is equal to c1 exponential, sorry, k square into g, then k square into g is equal to 1 by r c1 exponential minus jkr. So these two terms go. Then that into dv or dqr, that is, so the left hand side is this much, that of integrated over dv. So dv is not visible here, you can write that part as dv, that will be equal to integration over the volume d cube r. Now you know integration from minus infinity to infinity, or integration over whole volume, or integration minus infinity to infinity of delta x dx is equal to 1. So using that, the right hand side is equal to 1. The left hand side is limit r goes to 0. Then the by integration, the first part will become 4 pi. From where we get 4 pi is simple. The volume integration is r square dr the sine theta d theta d phi. Now integration over d phi gives us 0 to 2 pi. Integration over d theta sine theta d theta in the limit 0 to 2 pi, that gives us 2. So 2 into 2 pi, that gives us 4 pi. Then integration over 0 to r, that gives us this much, minus c1 and jkr plus 1 into exponential minus jkr. This is a simple integration that you can easily do. So on that we are not going to repeat, that you can do easily. C1 jkr plus 1 into exponential minus jkr. Similarly, for the second term we have minus 4 pi remains as it is, k square integration from 0 to r exponential minus jkr r dr. Now put the limit on both these things. In the second term, when we put the limit r goes to 0, the second term in that limit goes to 0. So that is 0 immediately. Once you put the limit r goes to 0, the second term integration 0 to r exponential minus jkr r dr, that is 0, that is equal to 0 when you put limit r is equal to 0. Then in the first term, the part jkr, that part goes to 0 as you put r is equal to 0. Then exponential minus jkr, as you put r is equal to 0, that becomes 1. Exponential 0 is equal to 1. So that leaves us in the first term, the integration is c1. So then 4 pi remains as it is. Therefore the first term now becomes minus 4 pi c1, that is equal to, and the second term is 0. So and that is equal to the right hand term is equal to 1, which means c1 is equal to minus 1 by 4 pi. So c1 will be of the form of 1 by 4 pi. So gr will be of the form 1 by 4 pi r exponential jkr, and that will be what is gr. Okay, next. Okay. So del square gr plus k square gr is equal to minus dqr is an inhomogeneous equation. This is a differential equation which is satisfied for the Green's function gr, and this is homogeneous everywhere except r is equal to 0. Therefore, del square gr plus k square gr is equal to 0, and we have solved that. Solving that, we have found out what is the value of gr. So if you solve this, then we will find out more information about gr. So we are going to solve this. The general form of the solution we have seen now. It will be exponential minus jkr by 4 pi r. This will be the general form of solution. Now what does that imply? Now if you look at the general form of solution, it has two terms, the numerator and denominator. Numerator is exponential minus jkr. Therefore, numerator part gives us the phase of gr, whereas the denominator part 1 by 4 pi r is the amplitude of gr. So, for a fixed r, if you look at this, this is symmetric on this is in spherical coordinate system, and it is symmetric around the origin. Since it is symmetric around the origin, which means you have the source at the origin, then Green's function is symmetric around the source. Now, as you go outward from the source, go a distance r from the source. So, r can be anything. Take a small value of r. So, that shows, that is the inner circle that we are showing. The inner small circle, on that circle, that actually is a sphere. And so, we have taken a cross section. So, we are seeing a circle here. So, on that sphere, everywhere on the surface of the sphere, the phase is exponential, phase is minus jkr. Exponential minus jkr gives the phase on the sphere, on the surface of that sphere, small sphere. So phase remains constant over that sphere, over the surface of that sphere, whereas the amplitude is 1 by 4 pi r on that sphere. Now, if I expand r, if I take a larger r, which is the outward circle, again on the outward sphere, outer sphere, again phase will be constant over the sphere, over the surface, and amplitude will be 1 by 4 pi r. So that will keep on changing. The amplitude will keep on decreasing as you go away from the source. Amplitude will be more on a point on the sphere. If it is nearer, as you go away, it will decrease. That is point number 1. Point number 2 is the phase remains constant over the sphere, spherical surface, which means this represents a spherical wave. When, as you know, what is a spherical wave? In the spherical wave, the wavefront means the points with constant phase. So that represents a sphere, the surface of a sphere. Since the phase, constant phase points are representing a sphere, it is a spherical wave. Next. So this is equivalent to the response of the potential to an impulse excitation that we already have seen, because the right hand side is minus dqr. So gr is equivalent to the response of potential to an impulse response. Okay. And a solution for the potential A is, once you know what is the Green's function, then we can find out the solution to the potential A. AR will be equal to on J R mu J R dash into G R minus R dash. We are going to convolve that. And so if you convolve that, we will get this mu J R dash into G R minus R dash dq R dash, or convolve it over the volume, that will give us AR. So that is what is AR here. So then we are going to find the general form of the solution. The general form of the solution will be GR, that we already seen. GR is equal to exponential minus jkr by 4 pi r. It is equivalent to response of the potential to an impulse excitation. and solution of the potential we have seen. So this is about the Green's function and how to find out the solution uh, for the potential using the Green's function. This is all about that. Then we will come to the next part, which is the Hertzian dipole. For the Hertzian dipole, remember this part. Uh, this is important. We'll assume that we are considering a point dipole. So dipole is localized to a point. So it is a point dipole. The point is located at the origin. Since it is source, the location is r dash. R dash is equal to 0. It is located at origin, therefore r dash is equal to 0. And the dipole is oriented along the z-axis. So its orientation is along the z-axis. It is time harmonic in nature. The time variation is of the form exponential j omega t. Then we have a dipole moment P. P is the dipole moment. For this dipole, P is the dipole moment. You know, if you have a dipole moment is P into dl if you have 2 points. But since you are considering this as a volume, therefore corresponding to polarization, that is dipole moment per unit volume, here since we are considering volume, so corresponding to polarization, that is dipole moment per unit volume, PR, capital P, dipole moment is small p, capital PR, that will be equal to small p dqr, delta qr. Delta qr is actually the Dirac delta function in the 3D. So PR is equal to small p Dirac delta, that into Dirac delta function of R. Now we are going to use the concept of dielectric polarization here. I am sure in the plus 2 level you have studied about dielectric polarization, which is different from electric field polarization. The field polarization that we have discussed, it is different from dielectric polarization. Let me revisit the dielectric polarization. Now for dielectric polarization, you remember that in the presence of an external field, so if you have external or free densities of charges rho and currents J in a material medium, then the molecules will be oriented in a particular fashion in the presence of a charge density rho or a current density J in a material medium. Once you impress a source, the source impresses a field. Because of the field, the molecules are oriented in a particular fashion. So this induces the dielectric polarization in the material. What induces the dielectric polarization? The presence of rho and J, or rho or J, either current or charge. Presence of rho, current or charge induces dielectric polarization in material. So what is dielectric polarization, capital P? That is defined as epsilon 0 into Chi into E. And Chi is called the susceptibility. So capital P is equal to epsilon 0 Chi E. Chi is the susceptibility, and the susceptibility in physical terms, it gives a measure of the electric polarization property of the material. This susceptibility gives a measure of the electric polarization property of the material, and by definition, this is the average electric dipole moment per unit volume. So susceptibility is the average electric dipole moment per unit volume. This presence of susceptibility, this manifests or results in electric flux density. So this results in electric flux density through these equations. The equations that we use to get the flux density is epsilon is equal to, epsilon is the dielectric constant or permittivity. Permittivity is equal to epsilon 0 into 1 plus Chi. This is the definition of epsilon. So epsilon is equal to epsilon 0 into 1 plus Chi. As you know, and D is equal to epsilon C, epsilon E. So D will write epsilon E. For epsilon, write epsilon 0 into 1 plus J. So D is equal to epsilon 0 into 1 plus J into E. So that is epsilon 0 into E plus epsilon 0 into J into E. Now on that you can write as epsilon 0 into E plus P, as we know P is equal to epsilon 0 into J into E. That is the polarization. So epsilon 0 J into E is the polarization. So therefore D is equal to epsilon 0 into E plus polarization in the material. So epsilon 0 into E plus P. D is equal to epsilon 0 plus E epsilon 0 into E plus P. Now if you encompass this part into the Maxwell's equation, what we'll get? We'll get curl B is equal to minus dou D by dou D plus J. So that we know curl B is equal to J plus, curl B is equal to mu 0 J plus dou D by dou T. J is the current density, small j is the current density. So and dou D by dou T, for D if we write D is equal to epsilon 0 E plus P. So dou D by dou T is equal to epsilon 0 dou E by dou T plus dou P by dou T. So put that. So curl B is equal to mu 0 epsilon 0 dou E by dou T, that comes from mu 0 into dou epsilon into dou by dou T of epsilon 0 E, that gives us mu 0 epsilon 0 dou E by dou T plus mu 0 J remains as it is. So on the second term, then plus mu 0 into P, mu 0 dou P by dou T. So from that we have taken mu 0 constant outside. So that is J inside is J plus dou P by dou T. Similarly, divergence of D is equal to rho. So from that we will get divergence of D is equal to rho. D is equal to epsilon 0 plus P. Therefore, divergence of epsilon 0 E plus P is equal to rho. Now, if I take rearrange that algebraically, I will get divergence of E is equal to 1 by epsilon 0 into rho minus divergence of P. So on these two are in the Maxwell's equation. So this is encompassing the polarization, dielectric polarization into the Maxwell's equation. So capital P we have considered into taken into the Maxwell's equation, and capital P we have already seen in the previous slide. Capital P is equal to small p delta R, that we have seen. Now on the current and charge densities, due to the polarization of the material, these two is J polarization is the current density, polarized current density, that is dou P by dou T, and the charge density is rho polarization, that is charge density, that is minus divergence of P. These two are the current density and charge density. So with that we will stop for today. In the next class we will consider Hertzian dipole, on the analysis of Hertzian dipole in details, and maybe we will start half-wave dipole. So please read about the analysis of Hertzian dipole in the books and come back prepared in the next class. Hertzian dipole and half-wave dipole will start in the next class. So we'll stop here.
Hello, sir.
Go.
Sir, this video is available in YouTube, sir.
Yes, this is
Hello.
available in YouTube. Yes.
Okay, sir.
It is available in
Because I
YouTube.
think, sir, I think one more time.
You want to revisit it. You can revisit it in YouTube, it will be available.